Thank you, everyone, for joining the EcoCast today. We are kicking it off right now. Here we go. With that, we already did the poll. So with that, I'm excited to introduce Vikram, who is a Senior Manager of Product and Solutions Marketing at Pivot3. Vikram, are you with us?
Hi, David. Yes. Can you guys hear me okay?
I can hear you great. Yeah, thanks for being on. Take it away.
Awesome. Thank you. So good morning and good afternoon, folks. My name is Vikram, as David mentioned. I look after solutions, marketing, and enablement initiatives at Pivot3. And really, from solution standpoint, we're increasingly running into big data analytics sort of opportunities where customers are looking for hyper-converged infrastructure, and they find some of our architectural features really beneficial. So I'm going to, for today's presentation, I'm going to essentially go through the high-level characteristics of what a big data analytics workload means, some of the evolution from infrastructure standpoint, some of the characteristics, what are the requirements. I'll then get into some of the Pivot3 architectural features that sort of optimize our infrastructure for a big data analytics sort of a deployment. And then we recently did some technical work and published a reference architecture for Splunk. So I'll go through some of those details and also highlight the results towards the end of my presentation. So that's for agenda. We also have George Wagner, my colleague who does product marketing, here for any questions and answers. So if you have any questions, George would be more than happy to answer those questions via the chat window. Thank you. All right, so making machine data usable, right, because that's what big data does. And if you think about analytics, business analytics in general, it's gone massive transformation over the last couple of decades. And I think, there are a couple of things that are driving this transformation. One of those is this notion of connected devices, right? The proliferation of connected devices really changed a few things. And then the second thing is in the last couple of decades, most organizations have pretty much become completely digitized. So you converge these two things. You have unusual data sources, and organization being completely digitized. Now you have a lot of data that's being created, which is not traditional data. It's very different sort of data than the traditional business intelligence. Traditionally, your business intelligence systems, maybe business objects or Informatica, they would typically take in tabular data. You would point them towards certain databases. Maybe it's your sales database, maybe it's your accounting database, and they can run certain queries on them. Fairly simplistic in some manners. However, the new data does not fit that model. The new data is coming from all of these devices in the forms of system logs and information that they're sending. Most of this is unstructured. And so we needed fundamentally different approaches to look at this data and to make sense out of it. And the traditional BI approaches were really backward-looking, right? They would tell you what happened last month or last quarter and not really provide you any real-time insights that can help you make more strategic, future-looking decisions. But with big data analytics and this sort of data coming at us in such a high volume, we can actually create analytics that are more real-time, that can provide insights that will help you optimize your strategy, whatever you're trying to do. So all of these data sources, big data platforms can essentially take data from these sources, process that data, and that data can be used to derive critical insights for many different reasons, right? So if you're an application delivery person concerned with how your application is doing, this data can provide you insights into how your application is performing at certain times, what parts of your applications are used more than the others, are there any contentions going on within certain parts of your application, help you fine-tune how users experience your applications. If you're an IT operations person, this can really provide you a lot of critical insight into what's going on in your IT right now, right here. And that can help you make decisions. Is there any contention about to happen? Are there any correlations that I can learn from and be proactive and avoid any outages? So that sort of things. The third one there is security and compliance, and I would like to give an example of Pivot3 there. Pivot3, working with one of our channel partners and a third-party software vendor with Splunk, we bundled up these solutions and started offering these other security and compliance solutions. Really, it's designed to look at your IT infrastructure continuously, analyze it, and provide you alerts if there is anything abnormal, if there are any security threats going on in the environment, so you can address the problem before it becomes an issue. Similarly, from business analytics, fine-tune your product pricing strategy, that sort of stuff. But the last one there, IoT and machine data, is, I think, the one that's going to drive a lot of growth and adoption for big data platforms. The notion there is that all of these machines are now connected and they're sending data, whether it's a manufacturing machine sitting on a factory floor or if it's a jet engine flying in the air. All of these machines are generating a lot of data and transmitting that data. And so looking at data, making sense out of data, can we optimize operations? Can we do some preventative maintenance so we don't have any outages? That sort of usage is increasing, and it's going to drive a lot of big data growth, is what analysts are also predicting. So really, big data allows you to look at your data universe holistically, make sense out of it, takes in different kinds of untraditional data sources, and really allows you to derive critical insights that can help you in a number of business areas. All right, so if you think about the infrastructure side of big data, though, what we saw right now was what it can deliver and what from application standpoint. But from infrastructure standpoint, big data in a short period of time has gone, quite a bit of transformation. So when these platforms initially became available for this sort of unstructured data processing, they were essentially built for x86 standalone server nodes, right? And that really allowed them to get started quickly using commodity standards-based hardware and start analyzing data. So standards-based x86 servers, they would use local storage on those servers. Resiliency, because these servers are not resilient by themselves. If one of the node goes down, the resiliency was really handled by application by duplicating data sets. It was, with a lot of physical deployments, it's an extremely underutilized infrastructure. You can think about it, say, in a deployment, you need 4 indexers and 3 search nodes. Now you would need actually 7 physical machines to run that infrastructure. So a lot of infrastructure, a lot of it is underutilized in this scenario. And there are performance challenges with this as well. As the scale grows and you have more and more nodes, it becomes unmanageable. So now virtualization came into picture, solved some of these problems, right? So you started virtualizing your compute elements, your indexers and search virtual machines on a compute layer using hypervisor. But from storage standpoint, now you can use shared storage. However, for shared storage, you may need many different storage subsystems to address the specific data needs of specific data buckets. You may need high-performance storage. You may need a scalable, capacity-efficient storage for long-term retention. And it utilizes shared SAN and NAS sort of storage to do that. And these storage, as you can imagine, can become complex, expensive. Many of these storage solutions were really not designed for virtualization, right? They were scale-up, dual controller scale-up architectures. So in certain high-density environments, those storage resources can become contention. Fast forward to where we are today, and now if you combine the best of both worlds, bare metal servers as well as the virtualized compute and shared storage, you have something called hyperconverged, right? So hyperconverged model now offers you a simple modular x86-based infrastructure that handles your compute needs as well as your storage needs by virtualizing the storage underneath that. So you don't need an external storage to do that. It's operationally efficient because you're just managing x86 boxes, and it's simple to deploy, operationally efficient to operate. And with our HCI solution that utilizes a policy-based framework, an intelligence engine to prioritize resources, this can be a great platform for applications that have different, diverse data needs. So we'll see that in some of the architectural aspects as we go through these slides. Okay, so I think we have a poll question. David, do you want to read it out, or how do you want to do this?
Yeah, let me read it out. So it says here, do you currently have or are you planning to deploy a big data analytics platform? So everyone out there in the audience, check out the slide window, and we would appreciate your response. I'll share the results with everyone here in just a moment. I'm curious to see what everyone is doing around big data. I know a lot of companies, as was said in the previous presentation, might have a big data problem, but just not realize it, or don't have any current plans to address it at this point. Are you seeing that a lot today?
Yeah, I mean, I think some of those are transitioning into big data analytics is what we're seeing. Most of these are, some of the big data analytics deployments in the past built on shared storage are coming off of warranty, and they're looking at new infrastructure. So I think it's all over the place what we're seeing. And I think your polls sort of represent that too.
I agree. It looks like everyone out there has voted. Let me share the results with you. And it looks like 21% says they have a big data deployment. 14% are planning to deploy a big data platform. 25% aren't quite sure yet, and 39% don't have any specific plans. What do you think, Vikram?
Yeah, I mean, this is sort of what we're seeing generally in our install base as well. And the good thing about our platform is, it can handle multiple applications. And so a lot of our customers who used us for, say, VDI or who use it for video surveillance and analytics are starting to look at us. And based on that, I think this looks representative of our install base.
Excellent, excellent.
All right. Thank you. So now, from infrastructure standpoint, I represent an infrastructure company, so I'm going to talk more about the infrastructure that you need as a foundation to build a solid big data analytics solution on top of. So from infrastructure standpoint, if you think about many of these big data platforms, whether they are whether it's Splunk or it's Cloudera or it's Hortonworks, many of those are essentially, you'll see data is coming in from a lot of different sources to these platforms, right? All of these devices are sending data simultaneously, concurrently at a very high rate, and that's usually called as ingest. So the application needs to take in all of this data, index all of this data, and write it to the storage. And it needs to happen at a fairly low latency for it to be effective, right? To be able to take in all of that data at the same time without without dropping any data. So you need scalable high throughput to be able to achieve that. And when I say throughput, it's on both sides, application side as well as on the storage side. You need to be able to take in all of that data quickly. You need to be able to process all of that data from compute standpoint, and you need to be able to write that data to disk at a very high speed, very low latency to accomplish this. Secondly, once the data is written, the data usually is searched. And so certain parts of your data are going to be searched more often than the others. The one that came in more recently are usually searched more often. And for these search queries to be effective, whether it's an application that's conducting the search query or an operator that's conducting the search query, they also need to be very high speed, very low latency. So you need that sort of high performance, low latency storage access here. It's not so much about ingest now, but it's more about the read performance of your data sets. So you need that. And then to make things complicated, typically these deployments gather a lot of data over time. And there are certain regulatory and compliance requirements that require companies to keep this data for a long time. So you need a storage that can also be cost-effective and scalable to handle that petabyte scale cold and frozen data, which is rarely searched, but you still need to retain that. So looking at this, right, these are the requirements for big data infrastructure are pretty extreme. They need to be high performance, low latency, not only from compute, but also from storage standpoint. But at the same time, they need to be scalable, cost-effective, to be able to handle all of that data that the organization accumulates over time. And so that's where I think our platform can make a big difference. So this is where I'm going to introduce you to some of Pivot 3's architectural differentiators. Really, I mean, if we want to boil it in a nutshell, I think this slide does a good job. Some of the largest HCI deployments are built on our infrastructure. For example, one of the large city metro organization runs their operations on top of Pivot 3, and they're handling somewhere close to 10 petabytes of data. And we have a number of examples like this, and this infrastructure, the way it's designed to work seamlessly and automatically rebalance, they don't need a lot of operational overhead. They don't need administrative overhead to keep this infrastructure functioning and performing the way it should. So in that instance where I mentioned about 10 petabytes of data, there's one storage admin that's managing that infrastructure. In terms of efficiency, whether it's compute efficiency or storage efficiency, we provide market-leading outcomes. We're able to boost our compute densities as well as our storage densities because of the way we have optimized our NVMe data path. And then from performance standpoint, the scale-out architecture that we leverage and the NVMe data path that we leverage, it provides overall performance for the applications about 2 to 3 times traditional HCI solutions. So with that kind of architecture, we can handle big data deployments quite well. It's got scale, it's got efficiency, and it's got performance. And so I'll take you through some of the architectural aspects that play a role in that. So first of all, the foundation of Pivot 3 solution is this distributed scale-out architecture that we've leveraged for quite some time. Really, what it does is as you can see in the image, you can cluster a number of nodes into one Pivot 3 cluster. Now, when you cluster these nodes, really we're not just virtualizing the storage, but we're aggregating pretty much everything that the nodes provide, right? From storage standpoint, we aggregate all the drives. That means every single virtual machine, every single volume that you create spans across every single drive that's in a cluster. Now, that's critically important in a deployment like big data, where you have to support high ingest rates, right? So we have a large number of drives taking in data and writing it to disk. And since we parallelize that across a number of drives in a hybrid cluster, which can scale to 12 nodes, or a flash cluster that can scale to 16 nodes, you essentially have 144 drives. And so every single VM, every single volume really benefits from all of those drives providing the I/O performance. We also aggregate parts of the RAM to provide a read cache. We also aggregate bandwidth. Every single node that you add really essentially adds 20 gigs of application bandwidth, 20 gigs of SAN bandwidth. So as you're scaling your infrastructure, because you have more data being ingested, you actually are scaling your bandwidth as well. The next critical element is, or built on top of this distributed architecture, is the parented erasure coding that we have. Erasure coding is our method, parented algorithm that protects our infrastructure from any failures. If a node fails, how do you handle redundancy? That's something that we do with erasure coding. Most other HCI solutions use something very primitive, like replicating data from one node to the next node in order to keep from failure, so that way you have an extra copy of data. We believe that's quite an inefficient way of doing it. If you see the graph there, the bottom two lines, the straight line graph, is the sort of efficiency you will get with that kind of data protection. At the same time, you will incur 2 to 3x I/O penalty, because every write I/O becomes either 2 write I/Os or 3 write I/Os. So you're wasting a lot of I/O capacity in that as well. With our erasure coding, we eliminate that I/O duplication, so that adds to performance. But more importantly, we start getting RAID-like efficiencies, and that's quite important when you have to retain data for 2 to 3 years. And then lastly, with our Acuity platform, we added this policy-based quality of service that utilizes NVMe flash tier to this architecture. And now we are able to prioritize workloads, assign policies to the workloads between policy 1, which is a mission critical, and policy 5, which is a non-critical. You can assign policies in the range of 1 to 5 to your workloads or to your data sets. And system is now intelligent, that it understands what the priorities are, it understands what the workloads or volumes are doing, and if they require any performance. And based on priority and based on the access patterns, we will prioritize resources, whether it's NVMe resources, or it's RAM cache, or it's SSD or SATA drives. In a hybrid model, there are 2 SSDs and 8 SATA drives. So we also prioritize between those resources. So all of that put together is this intelligent multi-tier architecture. You can prioritize and have a hands-free policy-based performance management that will always meet your SLAs. So now you can have different policies, for example, for your hot, warm bucket, data bucket that's ingesting a lot of fresh data and a lot of data being searched, and you can have different policies for your frozen buckets, and that way you can make sure the right data set gets the right performance here. Just to go into a little bit more about this NVMe architecture that we have in our Pivot 3 Acuity hyperconverged infrastructure. So we leverage NVMe and NVMe flash, and it's a standard. You can put NVMe flash in pretty much any server today that has PCIe slot. What we are doing on top of it is actually what makes a lot of difference. We are smartly managing that NVMe. We are using it as a persistent tier of storage as well as a cache. We are making sure the right data sets are moving in and moving out of NVMe at the right time, so we can make the most use of NVMe resources. NVMe resources are ultra fast, but they're also not very scalable at this point, right? I mean, they're expensive, and you can scale them only to a certain extent in a node. And so given our ability to decide what needs to be in NVMe and what needs to come out of NVMe and when that needs to happen, we can really get a lot of performance out of it. As a result, we can boost VM density by 2 to 3x. We can provide better I/O performance as well as application performance. And so all put together, the intelligence working on top of NVMe is what is driving this superior performance. So the quality of service in action here, you can see why quality of service matter. And without the quality of service, what you see is on the left side, HCI without quality of service. And this has been a problem that's been plaguing a lot of IT organizations, and this has been preventing them from really using either a shared storage or a hyper-converged infrastructure to consolidate multiple mixed workloads. Right? What happens in this case is you cannot prioritize a workload, and the wrong workload ends up sucking up all the resources, and the right workload suffers. In our case, you can prioritize them. You see on the right-hand side. You can say order database. Think of it as maybe a heartworm bucket here in big data context. Is my mission critical, and you have business critical, and you have non-critical buckets. Now, if my mission critical workload is not driving any IOs for storage, then my system will allow other workloads who require the access, who want the access to get that performance. But as soon as my mission critical workload starts to experience more IOs, it will throttle the system and prioritize the resources and make sure the right workload always meets the priority, always meet the service levels. So it's a hands-free way of making sure how you prioritize the applications and make sure your right applications are going to get performance no matter what the situation is. And there's essentially in many use cases, we were completely able to eliminate any performance optimization that goes on an ongoing basis. Now, coming to Splunk, we recently published this reference architecture. It uses our new Acuity HCI systems. We did it on a hybrid system because hybrid system is what we feel is cost-effective for big data analytics. And the way we are looking at NVMe data path, it really does provide terrific performance for search and indexing activities. So what we were able to see in this one was about 4 to 6 times the indexing and search performance compared to what Splunk reference hardware recommends. So we were able to boost performance essentially by optimizing I/O performance and making sure that the CPUs are not waiting for storage to serve IOs, and that way you can more efficiently fit in more VMs, and fewer VMs can actually do more searching and more indexing. Some of these statistics I'm going to talk about on the next couple of slides, but really, if you're interested in this reference architecture, email your request to me. My email address is right here, and I'll be happy to send you the reference architecture. So here's a rough depiction of how the architecture was built, and the point here is it was exceptionally simple to build this architecture and to make sure it performs the way it's supposed to. You have indexers and your search head. If you have any analytics software, you can also deploy that on the same nodes as your Splunk software. In this case, this is a Splunk reference architecture. So, our quality of service can allow you to have multiple sorts of workloads, right? Search heads, indexers, as well as your analytics. In the case that I mentioned previously, malware bytes, they all could coexist on our cluster. You can prioritize them. And when it comes to your data buckets, you essentially really create your data buckets and assign them policies. You're going to have a few, hot and warm buckets. They're going to be relatively small. You assign them policy 1. That way your indexing operations are always going to get priority. You may have a cold bucket that may retain a month or 2 months or 3 months worth of data. You can assign it a policy 2. And that way, they will be prioritized after the indexing activities. But if the indexing activities are not going on, then your cold bucket can get a lot of performance. And then a frozen bucket can be on a non-critical policy because frozen bucket is usually not searchable. It's just a data retention, and that way you can cost-effectively optimize where your data lives. So flexible architecture here, what's key about it is flexible over time as well. You build it, it works based on policies. There's very little performance optimization you have to do over time. But as your needs change, for example, you have an audit happening and you need to make a data that was generated 3 years ago available for searching, you can simply flip policies on our volumes here. With our policy-based quality of service, you can flip simply on the fly, make policy changes, and make that data available. Now it's at policy 2 and 3. it's available, utilizing some of the NVMe resources to make sure your searches are more productive. So very flexible architectural, operationally simple to do, easy to scale. You can add nodes as your capacity needs grow. So what were we able to achieve with this architecture? So here are some of the results. So Splunk, generally the results are looked at. You look at indexing performance, how fast you can take in, index and store the data, and then you look at search performance, how fast you can search the performance. What I'm showing you here on the left side here is the indexing performance that we were able to achieve is enough on a 3-node hybrid system, was enough to support up to 13 terabytes of indexing per day. Now, in my practical experience, I haven't seen a deployment that would use that kind of indexing. I haven't really seen a deployment that would use more than a few gigs of indexing in a day, more than a terabyte of indexing in a day. So this is quite a high. Pretty much, any large big data indexing needs you may have, 3-node cluster may be able to satisfy it from performance standpoint. Now, you may need to add more storage just to retain all of that data that's coming in, but from performance standpoint, 3-node cluster can very effectively and safely index up to 13 terabytes on our system. Now, what you see on the right side is the search performance, and search performance is measured for different kinds of searches: dense, sparse, and rare. Dense means there's a larger concentration of data to be searched versus the total data available, and it goes down from there on. Across the board, we were able to achieve great performance benefits, performance improvement compared to what Splunk recommends or suggests you should get. So platform does awesome from indexing as well as from search performance standpoint, and it's very simple to deploy, simple to manage, and simple to operate. Did we have a polling question here?
Yes, sir. We do have a poll. Let me pop that poll up for you.
Okay, awesome. Thank you.
So the poll should be on the screen. It says, if you're currently having or are planning to deploy a big data analytics platform, what infrastructure are you considering? So the choices are just standalone physical hosts, virtualized servers, and a separate SAN or NAS, hyperconverged infrastructure, not sure or not applicable at this time. So I'm curious to see what the responses are on this. Let's give the audience here a moment to answer. All right, I see some responses coming in. All right, looks like most of the audience has voted. If you haven't, get your vote in now. Let me share the results.
Yep.
And the results are 5% just standalone physical hosts, 32% virtualized hosts with a SAN or NAS, 26% hyper-converged infrastructure, 21% not sure yet, 16% not deploying. What do you think, Vikram?
Yeah, I think the first one, right? A lot less people today are running it on standalone server. That's a change since the beginning days of big data when it was exclusively standalone x86 servers, right? So that's expected. I think people are moving towards newer technologies to simplify their infrastructure. The second one, you see there virtualized servers, separate SAN NAS storage. A lot of these maybe, I think, deployments that are already in place, came probably before HCI and maybe coming up for renewals and stuff, and may start looking at HCI as infrastructure. And I think what you're seeing down there under hyperconverged looks like a good number to me, 26%, who may be looking at these deployments for the first time or as a new deployment.
Yeah, absolutely. I agree.
Yes.
Did you already? Go ahead.
Yeah, I got one more slide, and then I'll take questions.
Okay.
All right. So this slide essentially, some of the technical features or aspects that we bring to the table. What do they do for a big data analytics sort of a deployment, right? So the low latency NVMe data path that we've optimized over time is really, provides you high indexing as well as faster search performance, and it really allows you to do all of that while slashing hardware, right? You may need less nodes with Pivot 3, and you may be able to get a lot better performance per indexer VM than other infrastructure. So you may need fewer VMs to do the same amount of indexing and search, and we saw that firsthand when we did our reference architecture for Splunk. We were able to get quite a bit higher performance, either it's indexing or search, per VM with a similar vCPU and RAM ratio, vCPU and RAM number, much better transactional performance out of that. The next one, really what we bring to the table is this multi-tier architecture, which is the first in HCI, and a policy-based quality of service, which I think is pretty advanced first in HCI, but I think compared to other storage solutions, it provides you very sophisticated resource prioritization, not resource reservation capabilities, which is quite important. And with that architecture, you really have one single infrastructure, right? You have Pivot 3 that can do your high performance search and indexing, but also do a long-term retention. So you do not need two different storage systems, one for performance, one for efficiency, right? Typically, you would deploy a high-speed flash system to handle your hot-warm needs. You would deploy a more scalable, low-performance, cost-effective solution for your cold data needs, and now you're managing two systems, sometimes three. In our case, you can do all of those data sets on one single Pivot 3 cluster. It's policy-based and it's hands-free. Once you assign the policies, the system will perform, and you can be assured of that. And it's flexible in the sense that you want to change those policies on the fly because there's a situation in your organization where audit is coming up or whatever else, right? Or maybe you want to look at your organizational data 3 years ago for your own business benefit. You could very easily promote the frozen data sets into high-performing data sets with Pivot 3. And then lastly, the distributed scale-out architecture and erasure coding really adds to simplicity in scaling. So, erasure coding provides you market-leading efficiency from capacity standpoint. So you have more usable storage per terabyte of raw storage that you buy. It can scale to petabytes. We have numerous examples using us at that scale very easily. And you can grow non-disruptively as your needs grow. You simply add in a node, and you have more storage, and the whole thing gets reaggregated again. And then you don't add capacity as needed in small steps. You don't have to plan your infrastructure for the next 3 years. You can add a node when you need it. It may be in 2 months, in 6 months, or in a year. Based on your data needs, when you need a new capacity, you can add it, and you can add it in a small step. You can add one node each time you need capacity. So it makes it really simple for you to grow your infrastructure as your data grows. And here's the question. Should I skip this one, David? Okay.
Yeah, we already answered that. So
yeah. And here's my information. If you have any questions, feel free to contact me there.
Excellent, excellent. I'll just leave that up while we do some Q&A. We do have some questions for you from the audience. If you're ready, Vikram?
Yeah, I'm ready.
All right. First one here, they're asking, what about quality of service policies for my storage? Can that be applied to data buckets, and is it based on virtual machines?
Oh, yeah. Yes, it can be applied to data buckets. So the quality of service policies, mission critical being 1 and non-critical being 5, and everything in between, can be applied at a data store or a volume level. You can design your buckets so that they're in those data stores. So we usually create a volume per bucket, and if you have 2 hot warm volumes, you would assign them quality of service policy 1. If you had let's say 4 cold data storage volumes, maybe you'll assign them quality of service 2 or quality of service 3. And then you may have 1 or 2 large volumes or multiple large volumes depending on your use case for frozen data, and you can assign policy 4 and 5. And the good thing about policy 4 and 5 is if you assign your data sets to that policy, it will not take up NVMe resources. And in that case, you're making sure that the data sets that don't need performance will not take up performance.
Got it. Got it. Another question here is about NVMe in Pivot 3. Is it used for data storage? Is it used for cache, or what's it for?
Yeah, it is. It's for both, and it is. You would not be able to create a data store and say tag this data store to NVMe, because that would be a very inefficient way of using NVMe. NVMe is really what we use. Our system uses internally. It uses at persistent tier, as well as parts of the NVMe are used as caching tier. So we manage that internally, transparent to the applications, and it's really the quality of service policies that govern what and how much NVMe is going to be used for what data sets.
Okay, nice. And if I want to do some automation and use some APIs, does Pivot 3 offer APIs?
Yes, Pivot 3 does offer REST APIs. So if there are any application integrations or you want to do integrations from automation standpoint, it's very easy with Pivot 3 to do that.
Okay. And what kind of server nodes are compatible with Pivot 3?
All right, so good question. So Pivot 3, we work extensively with two key vendors right now, Dell and Lenovo. We recently started supporting a lot more form factors. Now you can choose between 1U and 2U form factors. We have now some of the high-density form factors as well. So Dell R730s, 740s. We support Lenovo's 3650 as well as the RS650 that came out recently. Some of the high-density models can go all the way up to 172 terabytes per node. So we provide various different form factors, either 1U or 2U. And then you have a choice of different drive sizes. That means the total node capacity, different CPU core configurations, different RAM configuration, and there are a couple of ways you can deploy Pivot 3 solution. One would be, you can buy Pivot 3 branded appliances from our channel partners, and then everything comes Pivot 3 branded, ready to go. Or you can work with our partners like Dell and Lenovo to source your hardware, and you can put us as a software only offering on top of that hardware.
Very nice. Very nice. Well, I think that's all the time we have for questions, but a great presentation. Thank you for being on the event today.
Thank you, David. Appreciate the opportunity.